Hello, my name is Irene Kuang, and today I will be talking about mechanical tilt-induced gradient fields for low-field spokes and hub permanent magnet MR imagers. I've no financial interest to disclose. Permanent magnet MR research has accelerated in recent years due to the declining cost of rare earth magnets and RF embedded systems hardware. For many potential applications of MR, such as point-of-care diagnostics and classroom experimentation, where image quality is far less critical than portability and low cost, low field MR of the order of tens to hundreds of millitesla, generated using these arrays of inexpensive permanent magnets, provides an alternative to expensive high field clinical scanners. However, these systems can be quite inhomogeneous in comparison to clinical superconducting magnets, and thus require additional engineering efforts to design gradient encoding fields for imaging. Strategies for this have included incorporating built-in readout gradients into the magnet design, as well as using gradient power amplifiers to drive tens of amps into surface coils. As recently demonstrated by Clarissa Cooley at MGH for a Halbach array, time-varying gradient encoding fields can be generated mechanically by rotating the entire magnet array. In this presentation, I will describe a method in which encoding fields can also be generated mechanically, but with much smaller motions in a spokes and hub-based permanent magnet. Our group has previously presented a calibrated equivalent charge-based simulation approach for optimizing B0 homogeneity in a spokes and hub topology, which is easy and safe to assemble and requires only inexpensive and commercially available permanent magnets that are slid into a 3D printed enclosure. Using a low-cost signal chain consisting of a microcontroller and ultrasound pulsar chip, we can achieve broadband RF excitation with a dithered pulse on the unshielded magnet to measure spin echoes with a 50 kilohertz bandwidth. As we just saw, the symmetry of the spokes and hub magnet produces a radially symmetric B0 field along slices in the Z direction within a desired 8x8 millimeter field of view. However, with a small quarter-degree tilt along the X or Y axis of one of the magnet hubs, or a total displacement of less than 200 microns, we can produce a spatially discriminating field gradient. The simulation here shows that this change in magnet geometry results in a departure from radially symmetric field patterns and the appearance of an approximately linear gradient field of 29 millitesla per meter when moving along the tilt direction. We validated these simulations by field mapping using an array of Hall effect sensors attached to a 3D printer. Looking at the field pattern along a diameter at the center slice of the magnet, we obtain matches between simulation and measured data with and without a tilted gradient. The gray shaded region indicates the desired imaging region. For a 2D map showing a slice at x equals 0, the field patterns match quite well between simulation and measurement, particularly in the imaging region. Summing the simulated B fields across our field of view, the orange curve shows a broadening of the frequency spectrum when a tilt is applied compared to the narrow spectrum in blue of the homogeneity optimized untilted magnet. To begin our experiments, we took an 8 millimeter diameter test tube filled with water and drove 100 kilohertz bandwidth RF pulses through a single channel unshielded solenoid coil with our ultrasound chip pulsar. Comparing the measured echoes, the frequency spectrum is broadened when the quarter-degree mechanical tilt is applied, as expected from simulation, and there's a narrowing of the time domain echo. As a preliminary demonstration of projection-based encoding, we used a phantom containing 2 adjacent tubes of water. When the tubes are placed horizontally along the Z-directed B field, there are 2 distinct peaks in the frequency spectrum when a tilted gradient is applied in the direction of the tubes of water. Consequently, when the phantom is rotated 90 degrees, there's no separation in the frequency spectrum as the phantoms are orthogonal to the applied gradient field. These results provide a proof of concept for imaging using a mechanically generated small tilt gradient field with our spokes and hub magnet. This method avoids the use of driving high currents through external gradient coils, and the handheld sized magnet used here shows promise as an educational tool. Because there are no heating or current limitations, this approach can also be scaled up in size for imaging and point of care applications. For the magnet shown here on the left, initial simulations show that a 3-degree tilt requiring less than a 5 millimeter change in magnet position can generate a 62 millitesla per meter gradient. And with that, I'd like to thank my lab mates, collaborators, and our funding sources, and thank you for your attention.